When lightning strikes near a transformer and the building's main breaker fails to trip, it indicates a potentially dangerous situation. Here's a breakdown of why this might happen and what steps should be taken. The master breaker may not have tripped for several reasons. Firstly, incorrect breaker size might be the culprit. The master breaker may not have been rated for the amount of current that flowed during the lightning strike. This overload could have prevented it from tripping. Secondly, a faulty breaker could be the issue. The master breaker may have been defective or damaged, which prevented it from tripping properly. Thirdly, a ground fault protection failure might have occurred. If the transformer had a ground fault protection system, it may have failed to detect the ground fault caused by the lightning strike, preventing the breaker from tripping. Fourthly, delayed tripping could be to blame. Some breakers have a delay built into their operation to prevent nuisance tripping during temporary overloads. If the lightning strike caused a brief high current surge, the breaker may have delayed tripping, allowing some power to reach the building. Fifthly, arcing fault could be the cause. The lightning strike may have created an arcing fault on the building's electrical system. This type of fault can prevent breakers from tripping properly. Sixthly, a utility issue could have contributed. It's possible that the lightning strike affected the utility's electrical infrastructure outside of the building. This could cause an interruption to the main power supply before the building's master breaker had a chance to trip. There are several consequences of the master breaker not tripping after a lightning strike. Firstly, electrical fires become a significant risk. Continuous power flow despite a fault can lead to overheating and potential fires. Secondly, equipment damage is a concern. Electrical systems that are not properly protected from surges can experience overloads or damage. Thirdly, safety hazards arise. Faulty wiring and unprotected systems can pose risks to occupants. If your breaker didn't trip, there are some recommended actions to take. Firstly, contact a qualified electrician immediately. They can assess the damage, repair the electrical system, and ensure that appropriate safety measures are in place. Secondly, inspect the building's electrical system. Check for any visible damage or loose connections. Thirdly, have the master breaker tested. Verify that it is functioning correctly and is rated appropriately for the building's electrical load. Finally, consider additional surge protection. Install surge protectors on sensitive equipment to safeguard them from future lightning strikes. To delve deeper into the subject, it's essential to understand how circuit breakers work. A circuit breaker is an electrical safety device designed to protect an electrical circuit from damage caused by overcurrent or short circuit. Its basic function is to interrupt current flow after a fault is detected. Circuit breakers are typically resettable, either manually or automatically, unlike fuses, which are single-use devices. There are several types of circuit breakers, each designed for different applications and voltage levels. Miniature circuit breakers, or MCBs, are commonly used in residential and light commercial applications to protect individual circuits. Multi-case circuit breakers, or MCCBs, are used for higher current and voltage applications in industrial and commercial settings. Air circuit breakers, or ACBs, are used for high voltage and high current applications, typically in power distribution systems. The tripping mechanism of a circuit breaker is crucial to its operation. Thermal magnetic circuit breakers use two different mechanisms to trip. The thermal element responds to sustained overloads. When the current exceeds the breaker's rating, a bimetallic strip heats up and bends, eventually tripping the breaker. The magnetic element responds to short circuits. When a high fault current flows, it creates a strong magnetic field that trips the breaker almost instantaneously. Electronic trip circuit breakers use electronic sensors to monitor current and voltage. They can provide more sophisticated protection features, such as adjustable trip settings and ground fault protection. When selecting a circuit breaker, it's important to consider several factors, including the voltage rating, current rating, interrupting capacity, and trip characteristics. The voltage rating must be equal to or greater than the system voltage. The current rating is the maximum continuous current that the breaker can carry without tripping. The interrupting capacity is the maximum fault current that the breaker can safely interrupt. The trip characteristics describe how quickly the breaker will trip under different overload and fault conditions. Ground fault protection is an important safety feature that protects against electrical shock hazards. A ground fault occurs when current flows through an unintended path to ground, such as through a person touching a live wire. Ground fault circuit interrupters, or GFCIs, are designed to detect ground faults and quickly interrupt the circuit, preventing serious injury or death. GFCIs are commonly used in bathrooms, kitchens, and outdoor areas where there is a risk of water exposure. Arc fault circuit interrupters, RFCIs, are designed to protect against arc faults, which are dangerous electrical discharges that can cause fires. Arc faults can occur due to damaged wiring, loose connections, or faulty appliances. RFCIs detect the unique characteristics of arc faults and trip the circuit, preventing fires. RFCIs are typically installed in bedrooms and other areas where people sleep. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning, power line disturbances, or switching events. SPD divert the surge current to ground, preventing it from damaging sensitive electronic components. SPD are typically installed at the service entrance of a building and at individual circuits. Regular maintenance of circuit breakers is essential to ensure their proper operation. Circuit breakers should be inspected periodically for signs of damage such as cracks, corrosion, or loose connections. They should also be tested regularly to verify that they are tripping properly. Testing can be performed using a circuit breaker tester which simulates overload and fault conditions. If a circuit breaker fails to trip during a test, it should be replaced immediately. Lightning strikes can cause significant damage to electrical systems. Lightning is a powerful natural phenomenon that can generate extremely high voltages and currents. When lightning strikes near a building, it can induce surges in the electrical system, which can damage or destroy electronic equipment. Lightning protection systems are designed to protect buildings from lightning strikes. A lightning protection system typically consists of air terminals, conductors, and grounding electrodes. Air terminals are installed on the roof of the building to intercept lightning strikes. Conductors carry the lightning current to ground. Grounding electrodes provide a low resistance path for the current to dissipate into the earth. In addition to lightning protection systems, surge protection devices can provide additional protection against lightning surges. SPD should be installed at the service entrance of the building and at individual circuits to protect sensitive electronic equipment. Electrical safety is paramount. Working with electricity can be dangerous, and it's important to take precautions to prevent accidents. Always de-energize circuits before working on them. Use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. If you are not comfortable working with electricity, hire a qualified electrician. Understanding the NEC, or National Electrical Code, is crucial for electrical installations. The NEC is a set of standards for safe electrical installations in the United States. It covers everything from wiring methods to grounding and bonding. The NEC is updated every 3 years to reflect changes in technology and best practices. Electricians and electrical inspectors use the NEC to ensure that electrical installations are safe and compliant. Some common NEC requirements include the proper sizing of conductors, the use of approved wiring methods, and the proper grounding and bonding of electrical systems. NEC Table 310.15b16 provides ampacity ratings for conductors based on their size and insulation type. NEC Section 250.122 specifies the minimum size of equipment grounding conductors. NEC Section 210.8 requires ground fault circuit interrupter protection for receptacles in certain locations, such as bathrooms and kitchens. Electrical grounding is the process of connecting electrical equipment and systems to the earth. Grounding provides a low resistance path for fault current to flow back to the source, allowing the circuit breaker or fuse to trip and clear the fault. Grounding also helps to stabilize voltage and reduce electrical noise. There are two main types of grounding systems: equipment grounding and system grounding. Equipment grounding connects the non-current carrying metal parts of electrical equipment to ground. System grounding connects the neutral point of the electrical system to ground. Bonding is the process of connecting different metal parts of an electrical system together to create a low impedance path for fault current. Bonding helps to ensure that all metal parts are at the same potential, reducing the risk of electrical shock. Bonding is typically accomplished using bonding jumpers, which are short lengths of wire that connect metal parts together. Electrical panels, also known as load centers or breaker boxes, are the central distribution point for electricity in a building. Electrical panels contain circuit breakers that protect individual circuits from overcurrents. Electrical panels should be properly labeled to identify the circuits they serve. Electrical panels should also be kept clear of obstructions to allow for easy access and maintenance. When working on electrical panels, it's important to follow safety precautions. Always energize the panel before working on it. Use insulated tools and wear appropriate personal protective equipment. If you're not comfortable working on electrical panels, hire a qualified electrician. Three-phase power is a type of electrical power that uses three alternating currents that are 120 degrees out of phase with each other. Three-phase power is more efficient than single-phase power and is typically used in industrial and commercial applications. Three-phase power requires three conductors, plus a neutral conductor in some cases. The voltage between any two conductors in a three-phase system is typically higher than the voltage between a conductor and neutral. Common three-phase voltages include 208 volts, 240 volts, 480 volts, and 600 volts. Single-phase power is a type of electrical power that uses a single alternating current. Single-phase power is typically used in residential and light commercial applications. Single-phase power requires two conductors, a hot conductor and a neutral conductor. The voltage between the hot conductor and the neutral conductor is typically 120 volts in North America. Electrical transformers are devices that transfer electrical energy from one circuit to another through electromagnetic induction. Transformers are used to step up or step down voltage levels. Transformers consist of two or more coils of wire wound around a common core. The coil connected to the source voltage is called the primary winding, and the coil connected to the load is called the secondary winding. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage transformation ratio. Transformers are used in a wide variety of applications, including power distribution, electronic equipment, and industrial machinery. A pole-mounted transformer is a transformer that is mounted on a utility pole. Pole-mounted transformers are typically used to step down voltage from high-voltage distribution lines to low-voltage levels for residential and commercial customers. Pole-mounted transformers are typically oil-filled and are designed to withstand outdoor weather conditions. Electrical meters are devices that measure the amount of electrical energy consumed by a building or appliance. Electrical meters are typically located at the service entrance of a building. Electrical meters measure energy consumption in kilowatt-hours. Electrical meters are read periodically by the utility company to determine billing charges. Smart meters are a type of electrical meter that can communicate with the utility company wirelessly. Smart meters can provide real-time information on energy consumption, which can help customers to conserve energy. Electrical codes and standards are developed by organizations such as the National Electrical Code, the Institute of Electrical and Electronics Engineers, and the American National Standards Institute. These codes and standards provide guidelines for safe electrical installations and practices. Compliance with electrical codes and standards is essential to ensure the safety of people and property.